So last time we talked about mutual exclusion and specifically how we address the problem of we had this race condition problem. How do we address it? Well, we need to somehow make sure only one thread executes a critical section at a time. So for that we have the notion of mutual exclusion. So we need to somehow implement this entry and exit sections. So, and there are certain conditions that we need to satisfy, so that no process stays in the critical section forever. That's one condition, right? And we will make sure that, well, I mean, this is the assumption I have to make, because, of course, sometimes, maybe buggy programs will violate it, but hopefully that's our assumption of when we implement this algorithm, right? So if somebody stays in the critical section forever, no one can enter it, again. So that's not acceptable, right? So, but otherwise, like, we'll make this assumption. So shared variables used in the entry or exit section are not accessed during the critical section and remainder section. So way we're going to implement entry and exit section, like, we'll use some special maybe global variables, but they shouldn't be used in the critical section itself or in the remainder section. So anywhere outside of this entry and exit section, they should not be used. So effectively, our idea is to protect the critical section with a lock. So when we, before we enter the critical section, we're gonna acquire the lock. And this is what we call entry section, right? And when we exit critical section, we're gonna release the lock. That is exit section. So another way to think about this problem is to kind of consider a lock, right? So something, a special lock which makes sure that only one thread enters the critical section. So also in our previous examples, we saw this atomic or something like that. That would be kind of analogous to having a critical section. So that's something that should be executed in a mutual exclusive manner. So just recall these examples that we looked at last time. There was when we have this data race, but there is also a race condition also, right? So how did we solve it? We had this first solution where we created like a bunch of atomic sections, right? And which is effectively critical sections. We saw the data race, but unfortunately there was still a race condition. Then there was finally when we created a critical section for everything, then there was no race condition. And you recall that sometimes it's also possible that you create this critical section but still access some variables outside of this critical section, and that creates a data race, even though there is no race condition in this particular example. So yeah, so the thing that we want to make sure is that one thing to keep in mind about the previous thing is data races can be detected automatically. So for data races, I can just go and run some tool, and that will say, okay, these two threads wrote this shared variable simultaneously without any protection, and that looks wrong. And that data race can be catched. I mean, I can catch it, right? So, but for race condition, not so much. I mean, there is no magic tool which will say, okay, there is a race condition, there is a flaw with synchronization, because there might be so many variations, and it's not really easy to detect race condition. So, and just because you remove data race doesn't necessarily mean that you removed race condition. And the example for this is, let's go back to this one, right? So when we had no data race, but race condition, we effectively created 3 critical sections. Seems like we don't have any data race. We don't access any of these variables outside of this critical section, but still there is a race condition. It's still the algorithm is incorrect. still it's possible that somehow you will end up with a negative balance. And therefore, if you look at this example, just because you got rid of data races doesn't mean that you can eliminate race conditions. In fact, it can even be dangerous, because if you just blindly remove data race, it can create some liveness problems. And that means in terms of like you can have like deadlocks, live locks, and so on. So those are concurrency issues that we will discuss later. So one thing to also be kind of mindful is you need to know when you what you need to exclude mutually exclusively and what you don't need to exclude mutually exclusively. For example, if we have a remainder section, yeah, that doesn't need to be executed mutually exclusive with the critical section, right? So that's because only critical section has to be protected. But on the other hand, when you have multiple critical sections, maybe this is when you want to consider what critical section and like whether you want to use the same lock or whether you want to use different locks, how you're going to protect it. Because let's go back to this example again. We have multiple critical sections here, effectively, right? So this atomic will effectively mark multiple critical sections. But just because I introduce critical sections here like this doesn't mean that I solve the race condition. So, you know, when later in the later example, we introduce a different critical section, which encompasses all this operation into one critical section, then we solve the race condition. So you have to be, you know, mindful about critical section, what you determine as a critical section, and whether you're going to use the same lock. And sometimes even use the same lock, just because, let's say, I'm using the same lock here and have three separate critical sections, still doesn't solve the problem. Only when I put it under the same lock, under the same critical section, it will solve the problem. So, any questions so far? Okay, don't hesitate to ask any questions. You can also send a chat message if you want. Yeah, so one way to solve one way to achieve mutual exclusion is to use to disable interrupts. So why wouldn't we just, so, and by the way, mutex is also an abbreviation for mutual exclusion, and more specifically, it's used as an abbreviation for the solution of the mutual exclusion problem for the lock, right? So very often you will see mutex, lock, those are kind of those terms are used interchangeably. So the first way that you can implement mutual exclusion is by disabling interrupts. So you disable interrupts, and then what? Well, if I disable interrupts on a uniprocessor system, then by doing so, hopefully I can prevent any like timer interrupts, and therefore I can prevent preemption, and therefore, you know, only when this thread is done, you know, unless I'm yielding time deliberately, but I can assume that I'm not yielding time when I'm in the critical section, then, you know, I shouldn't have any issue, right? Because I won't have a switch to another thread because there is no preemption during that time. And not to mention that the interrupt handler will not do something simultaneously also. So there's another issue we have to consider, that the interrupt handler can itself access the same resource. But, you know, assuming that I have disabled interrupts, I can potentially solve this issue on a uniprocessor system. And in fact, it's used to some extent inside the kernel. So it's not completely, it's even though it's trivial and it's not acceptable in every case, but it's still occasionally used. But it's not generally useful. So what if we have a trap occurs when the interrupts in disables? And by trap, when we disable interrupts, we typically also disable traps, because there is like CLI instruction in x86 will disable both interrupts and traps. And so that means you have like maybe some page fault, maybe you have some lazy allocation or something going on, or maybe you need to bring something from disk. So you disable traps while you're in the critical section. Then you have to be careful about what memory you accessing, then what if this memory is not there, like what if this code is not there. So generally not very acceptable. And not to mention that you cannot disable interrupts from user space, right? So it's possible to do it from kernel space, but from user space, at least on x86, that is not generally allowed. And certain interrupts can also be non-maskable. And by non-maskable, what I mean is that, there is a general term. Non-maskable means that something that cannot be, some maybe fatal error that happens in your computer, maybe there is some memory issue or something like this. So the interrupt that you cannot disable effectively, that you have to handle. And so what happens to them, right? So because we can still have non-maskable interrupts. But assuming that nothing like this happens, I have a control. Maybe I'm just using the kernel space. This kind of lock is only used in kernel space, and assuming that I know what I'm doing, this like pages are not on the disk, so they are in memory. So there shouldn't be any trap happening or anything like this. I'm not executing any invalid instruction. Then maybe it's acceptable in certain cases. And it's efficient only for really small critical section. But another problem with this approach is that it will work on a uniprocessor system, but generally for multi-core system it will not work, because now you have interrupts and traps happening on different cores, and therefore you still have potentially the same issue. Another thread is scheduled on a different core or preempted on a different core or something like that. So it's again, it's not going to be generally useful. So how do we implement mutex without disabling interrupts? By the way, if you have any questions, don't hesitate to interrupt me. So how do we disable interrupts? How do we implement mutex without disabling interrupts? Well, it's actually not that trivial, unfortunately, because let's look at one solution, which is not correct, but let's take a look at the solution nonetheless. So how about if we construct a lock, like a special variable, which will be a Boolean flag, and it will be basically set to 1 or 0, true or false, and we will just wait until this flag is set. That means somebody is in the critical section already. When we exit the critical section, we will reset lock to 0, and then when we enter, we set it to 1. So effectively, we have the busy wait loop while lock is 1. So it means somebody has taken the lock already. Okay, so then somebody releases the lock. We grab the lock. We set lock to 1. Enter the critical section. So while lock is 1, other threads should be, stuck. They will see that while lock is 1, they will not be able to enter the critical section. Finally, you reset lock to 0. Somebody else will be able to enter. At least that's our hope, right? So, but unfortunately, it's not true. Why is it not true? Can anyone give me an example why it's not true? Anyone? Anyone want to volunteer? Okay. Yeah, so let's say yeah, okay, let me kind of first approach that and explain it informally, right? So if you look at this while loop, you can see that there is a gap between this while loop and the place where we set lock to 1. So there is some gap, and that's a problem. If there was no gap, and we'll look later at one example where we can, with a special hardware support, we can avoid this gap. But if there is a gap like this, what may happen? So while I'm checking the lock, okay, maybe some other thread previously set lock to maybe lock was initially 0, right? Okay. Then some thread got a lock. Okay. Wants to get then another some thread trying to get a lock, right? Trying to get a lock. So it's checking while lock is 1. Well, lock was 0, therefore it will not wait. So it will immediately break from this loop. And let's assume the thread will get immediately preempted after this. It didn't set lock to 1 yet. So it checked that lock was not 1. So therefore it broke from, I mean, it's no longer in that loop. But now it didn't set lock to 1 yet. So it's about to set it later. So it got preempted. So another thread in the meantime got scheduled, and it also sees that lock is still 0 because lock was not set to 1 yet. So therefore, it's also not going to wait in this while loop. It's also going to see that lock is 0, so it can finally enter the critical section. It will set lock to 1 and enter the critical section. Yes, so then what will happen is that then maybe another thread, original first thread, will get resumed. And at that point, that thread will find that, okay, I can finally set lock to 1. Because that's the next instruction that I need to execute. And even though the second thread was already in the critical section, it will set lock to 1. So now 2 threads are in the critical section. So, and this is something that is clearly not what we expect. Because of this corner case, when something can get preempted in this gap, now we have 2 threads in the same critical section, and that's really bad. Because now there is no protection, because now no mutual exclusion that we're trying to achieve. So that is a problem. Okay, it says doesn't work. Any questions about this example? You don't hesitate to ask any questions. I know that today we have it remotely, but don't hesitate to maybe send it in the chat or ask like whatever is more convenient for you. Okay, so this doesn't work. So what can we do then? Well, I mean, putting aside that we can have some hardware support, which we'll discuss a little bit later, there is some software solutions to the mutual exclusion problem. So what we can have is some, purely algorithmic solution which just uses loads and stores. But it will have some additional assumptions. So there is assumption, for example, that we use a sequential consistent memory model. So this is not on our syllabus. That's something you can read on your own if you are curious. And if you are curious really about these different memory models, let me know. I can point you to some reading material. Just let me know. But the point is here that modern computers, modern CPUs don't actually support sequential consistent memory model. There is a way they can enable sequential consistent memory models by using so-called memory barriers, but typically they support much weaker memory models. And especially when we have multiple cores, what will happen is that the construct load and stores can be reordered, and so because of these issues, you may no longer have you may no longer see like something that is kind of no longer it makes sense if you look at this process, processor in isolation from the overall picture. But if you look at the overall picture, those things don't make sense because it seems like you reordered some instructions. And that is the problem. And not to mention that even compilers can reorder sometimes instructions if there is no data dependency or control dependency. It can really reorder it. And that can be an issue. But it's possible to solve it nonetheless. It's still, even on x86, which provides a relatively strong memory model, it's not fully sequentially consistent. There is a way to, it's still not fully sequentially consistent, but there is a way to enable it. So you can basically use some special memory fence after write, and that will enable it. But at that point, it may not be, the algorithm will be probably not that useful anymore. Still, we want to consider these algorithms because they're classical algorithms. They also introduce us to these concurrency problems, and I think they are very useful to look at. So the first solution to the problem is the so-called Peterson solution. So it's for two processes or two tasks, to be more precise. But in general, it can be actually generalized because it was initially presented for two processes. But as far as I know, it can also be generalized. But we will also consider two processes in our example. So also we will just assume that a load and store instructions are atomic. That means either they succeed or they don't, right? And we also can assume that there is sequential consistent memory model, but nothing is kind of reordered. All loads and stores in the same order as we kind of expect them to be. So we will have two processes or two tasks that share two variables. So the first variable is the turn variable. The second variable, the second shared variable is an array of Boolean flags. So there is a flag 0 will belong to the first process, and flag 1 will belong to the second process. And turn also can be above 0 and 1, depending on the which turn it is. Remember, we just have two processes in this example. I mean, again, it can be generalized, but let's look at the two processes. The variable, okay, so the flag array indicates that the process is ready to enter the critical section. So if flag y is set to true, that means py is ready to enter the critical section. It doesn't mean that it will enter, but it indicates its readiness to enter the critical section. And then the turn variable will say, okay, that's my turn, or that's another task turn, and so on, right? So it will just indicate the ID of the task. Like Bill said, okay, this task this task turn to enter the critical section. So the idea here, again, remember that we have just 0 and 1, so I and j can only be 0 and 1. So we have an algorithm for process py. So it says flag y equals to true, and then turn is j, so it's the opposite, right? So if you have I is 0, then j is 1. If I is 1, then j is 0, and so on. So then you wait while flag is j. So that's a different process. So my process is I, and j is a different process. So I kind of said the turn, it's a turn of the second process, so the opposite process. And then I'm waiting, okay, while flag is j, so it means while flag is j is true. So another process in the critical section, or at least indicated its preference to enter the critical section. And then end turn equals to j. So then I'm waiting. So that you see the semicolon means I'm not entering the critical section. So finally, when any of this is not true anymore, I'm going to enter the critical section. And at the end, when I want to release the lock, I will call flag y equals to false. So I'm no longer indicate my preference to be in the critical section. I set it to false. So if you look more precisely, this is what we get for P0 and P1. We have flag 0 set to true, turn set to 1, while flag 1 is true and turn equals to 1, then we are waiting. So for P1, it's the opposite. Flag 1 equals to true, turn equals to 0, while flag 0 equals to true and turn equals to 0, then I'm waiting. So yeah, so it may be a little bit confusing when you look at it. Before we go and break it down, let's also kind of clarify one more time. So the first part is the querying lock. So flag 0 equals to true, turn equals to 1, and whatever while loop. That is a querying lock. It's an enter section. And the exit section, the releasing lock, is when we set flag to false. So that's relatively simple, right? Okay. So now let's look how this works. So when P0, so our goal to prove that that P0 and P1 cannot be both inside the critical section simultaneously. So let's look at P0. So P0 is in its critical section. So if P0 is in the critical section, then then either of these two conditions must be true. So the first condition that we have, while flag 1 is true. So what if the flag 1 is false? Then I'm immediately going to break from the loop and enter the critical section. So that is the first condition. So that means flag 1 is false, right? So that's the first condition. That means that P1 is no longer in the critical section. P1 has left the critical section, flag 1 is set to false, or maybe it never entered the critical section because the initial value was false also. So that means it's no longer in the critical section, and therefore there is no problem, right, with this case. So we can already see that P1 is not in the critical section. So now there is another issue, right? So let's say flag 1 is true. When can it happen? Well, let's say P0 and P1 came almost simultaneously. And P0 set flag 0 to true. And P1 set to flag 1 to true. So it also indicated its preference to enter the critical section, but it didn't enter yet. So then you have in P0 condition while flag 1 is true, which is now going to be the case, and turn equals to 1. Okay, so now we have this turn variable. So now we have this turn variable. So what does this turn variable is doing? What is it doing? So the turn variable, for us to be in the critical section, either flag 1 has to be false. That we already considered, right? Flag 1 is not false. Flag 1 is true. Therefore, the only reason for us to be in the critical section, the turn is not 1 for P0. That means turn is 0, right? So that's the only way we can enter the critical section. Okay, how comes turn is 0? Well, that means P1 was in the entry section. So it was about to enter the critical section. It was in the middle of this operation, right? It already set its preference to enter the critical section. So P1 has already set flag 1 to true. But then it also set turn to 0. Now it's kind of make like some sort of self-sacrifice. It says, okay, you can go ahead and execute the critical section P0. I'm yielding to you. So it's like they're acting as like a good gentleman, right? So like trying to P1 is saying, okay, you can enter, and P0 says, okay, no, you can enter, or something like this, right? So they're yielding to each other, so to say. And then in this case, P1 was in its entry section, but it decided to let P0 go, right? So because it set turn to 0. And therefore, it's unable to proceed beyond the entry section. So why is P1 is unable to proceed? Because flag 0 is true. That is correct, because P0 is also inside the entry section, at least, right? Or maybe it's already in the critical section. So flag 0 is definitely true. Turn equals to 0. Yes, because we have just set it to 0. Because P1 has just set it to 0. So therefore, flag 0 is true, and turn is also 0. So therefore, I'm stuck in this loop. P1's made the sacrifice and got stuck in this loop. So on the other hand, because turn is now 0, P0 can break from this loop and enter the critical section. You see, P0 initially set turn to 1. So initially P0 was also stuck in the loop. But because P1 set the turn variable later, now turn is 0, and now can finally break from this loop and enter the critical section. But P1 at the same time cannot enter the critical section. So that's how it works, right? So, and you can also do the opposite. It's true. Let's say P0 came a little bit later after P1, then it will, make a sacrifice, so to say, right? So it will set turn to 1 and will allow P1 to break from that loop. So this is how we deal with this corner case when both threads are competing for the same lock. So they're yielding effectively to each other. So why yeah, so let me ask a question, and that may be something that helps you better understand how this works. What condition can we have when both tasks are trying to get a lock? So they, let's say flag 0 is set to true and flag 1 is set to true. So they're trying to get a lock. But is it possible that, you know, one thread is preempted or something happened to the thread, so it's no longer, I mean, it's no longer active. It's no longer actively doing anything. And the other thread is unable to enter the critical section nonetheless. So the other thread is not actively competing. Yeah, it still was in the intersection, but got preempted. Can it be the case that now, let's say P0 cannot enter the critical section? Any guesses? Yeah, by the way, I want to double check that you can hear me.
I can hear you.
Okay. Any guesses? Okay, let me explain that. Yeah, so let's say P0 set flag 0 to true, and P1 set flag 1 to true. And then maybe P1 got preempted. Just preempted, and that's it, right? Didn't set turn to 0, it got preempted. Just gonna settle later, but who knows, maybe it will be only resumed after 1 hour or something like this. So now P0 sets flag to 0 to true, turn to 1, and then what will happen? It will get stuck in the loop. It will say, while flag 1 is true, yeah, that's correct, because P1 has just set flag 1 to true. And turn equals to 1. Yes, and that's unfortunately is also correct, because turn equals to 1, P1 didn't reset it to 0 yet. So because P0 has set turn to 1. So therefore, I'm going to get stuck in this loop until P1 finally resumes and make the sacrifice, so to say, and set turn to 0. Only after this P0 can proceed. So because P0 effectively is waiting for when both of them are competing for the same lock, it's effectively waiting for the other task to give it a green light to go ahead, right? But the other task got preempted and doesn't give this green light, and therefore it's got stuck in this loop. So, and that's gonna happen until P1 is still descheduled. When P1 is finally scheduled, it will reset turn to 0, and now P0 can break from this loop. So P1 made the sacrifice, so to say, and then it will get stuck itself in the loop, because now turn is 0 until flag 0 is reset to false. So this is how it works, right? So general idea is that you want to make sure that a flag, like you have this flag condition, this is kind of similar to what we had before, but then there is a corner case when two threads are competing for the same um, thread, right? So two threads are competing for the same critical section. Then we have the turn variable, where each task effectively gives a green light to the other task to say, okay, you can enter. So this is how we break from that loop. But only one of them, when we have this condition when multiple threads competing for the same critical section, only one of them will be able to break from that loop. So it's a little tricky, but I suggest to go to just review that one more time, and particularly ask the same question that I asked. So what will happen if P1 is preempted after flag 1 is set to true? So that what happens to P0, because this point P0 is stuck. And that's so, not so much to show some weaknesses of this algorithm. Yeah, it's certainly probably not very desirable if one thread gets kicked out, like gets preempted in the middle of the enter operation. It blocks all other threads. That shouldn't normally happen. We want to avoid this because there is no reason why P0 cannot enter, because P1 is maybe gone for a while, right? It's not going to be back anytime soon. So why P0 cannot enter the critical section in the meantime. So it may be a kind of example of weaknesses of this algorithm as well, right? But it doesn't mean that it's incorrect, but it certainly has some disadvantage because neither of the thread is in the critical section right now, right? In this corner case. It's still we achieve mutual exclusion, but maybe sometimes some threads are waiting, even though they shouldn't be waiting, right? Ideally. Yeah, so that's something to keep in mind. But I made this example not so much to show the weakness of the algorithm, but to make sure you understand how this turn variable works. Okay, any questions so far about the previous algorithm? Yeah, again, don't hesitate to ask any questions. So let's look at the another example. So we another example is, like, you probably heard about this guy Leslie Lamport. He works at, I think nowadays, is Microsoft Research. There's a Dijkstra Prize, Turing Award. So those are highest awards, right? The Turing Award is like Nobel Prize in computer science, right? Yeah, so I mean, there is no Nobel Prize for computer scientists, unfortunately, but there is Turing Award. Yeah, so he designed the bakery algorithm, and so he's also known for his work in fault tolerance. There's a lot of papers, classical papers. He also known for LaTeX. So yeah, so probably I've heard at some point about this guy, right? So yeah, so let's talk about the bakery algorithm. So that was invented in 1974. So the algorithm allows to get a mutual exclusion. So everyone makes progress in this algorithm. So again, the same issues also still exist in terms of sequential memory model, but we will assume that's not an issue right now. So we have n shared variables, right? So we have an array of, well, it should be set to n, but let me clarify what it means. Choosing an array of n variables. So for each task, you're going to have its own entry, right? So you're going to have its own array and place, right, for each task. So that will indicate whether a thread will do some, we'll talk about choosing later, but it's just a Boolean flag when a thread will choose the ticket number. So it will be true while it's choosing and false elsewhere, right? I mean, yeah, so that's just a Boolean flag. And then there is a number. So the number is an integer. It's again an array, which will gonna have its own entry for every task. So initially it's 0, but otherwise it's going to represent a ticket number that corresponds to the current task. And by ticket number, I mean, let's say you came to some line and you want to enter maybe some room or something like this, but you have to stand in a line. You get a ticket. Maybe it's like, maybe you got to a post office, I don't know, maybe to other places where you get this ticket and have to wait in a line, right? So when they finally call your ticket number, then you enter. So that's the same idea here. So you get the ticket number, and for your current ticket number is stored in this number array. So initially 0 is when you don't have any ticket, and then it's going to be greater than 0 otherwise. So the bakery algorithm is it works like this, right? So you have this choosing variable, as I said, you have to set true and false, right? So we will talk about this in a moment, but just you can ignore that for a second. Then we have select number, ticket number. How do we select a number? We scan all current ticket numbers. We find the highest ticket number that we have. Let's say the ticket number 9 is the highest, and then we add 1. Then we get, let's say, 10, right? So that is our ticket number that which we're going to record in a number. And then we have a loop. Again, let's skip choosing for a second, and then we have a number, right? So we have to wait for our turn. So we'll yield every preceding thread with the smallest ticket to go first, and then we go after this. Finally, this is like a high level overview, right? And then in the exit section, we will reset our ticket to 0. So we are no longer in the line. We can set ticket to 0. So again, let's forget about this choosing variable for a moment. So then you can see that what you need to do is to choose the ticket number. So as I said, you just can get the highest number. Get the highest number across all tasks. So let's say you have task 1 has ticket 5, task 2 has ticket 3, and maybe task 3 has ticket 7, and maybe you are trying to find the highest. Okay, it's the 7, the highest, and then you add 1, you get ticket number 8. That's your ticket number. So you're going to be after everyone who's already there. And that ideally should be done atomically. Of course, we cannot do that atomically, but let's for a moment assume it's done atomically. So that means I can scan, see like simultaneously everyone's ticket and add 1, right? And I do that atomically. Of course, I cannot do that because it's multiple operation. I have to go to one person, check the ticket number, another person, check ticket number, another, and so on. And then I only after this, I'm going to add 1. But let's assume that I can do somehow this atomically, just using just by having one look at everyone, and I see everyone's tickets and add 1 simultaneously, right? Then in the loop, I'm going to check this following condition. While number j is, so I'm going to scan for every task that I have in the system from 0 to n and check their number, ticket number. If the ticket number is greater than 0, why is it greater than 0? Well, because if it's 0, that means there is no ticket. This task is not interested in the critical section, and we shouldn't even look at it. So because when we exit, we set number to 0. So therefore, we're only interested about the tasks that actually have a valid ticket. That means they have number greater than 0. Okay, and the second condition is number j is less than number y. So that this ticket, my number is number y. Other task has number j, right? So that's I'm scanning all other tasks in the system. If their number is less than my number, so if their ticket is before me, then they should go first, and I'm going to be waiting. So while this is true, I'm waiting. The moment that this number is no longer, valid ticket, it's reset to 0, then I'm not going to be waiting anymore. But otherwise, I'm waiting. Okay, so that's straightforward, right? So that means if I can get the ticket atomically somehow, then, there is no problem. I can just wait for my turn, and, then it's fine, right? I will yield to everyone else who is before me. But we don't see any issue with this, right? Because if you have, I'm yielding to everyone. Let's say I have a ticket number 10. I'm yielding to everyone who has ticket 1 to 9. And let's say it's someone who has ticket number 5. They yielding everyone from 1 to 4. And, you continue recursively. You can get to the point that only one thread is active right now in the critical section. Because everyone else is yielding to you. So, but how do we deal with non-atomic nature of finding the maximum number? Well, so how do we do that? Well, the point is there are two issues here. So if it's non-atomic, what can happen is that I can have this multiple tickets at the same time. So someone comes and finds the maximum, and they say, okay, ticket number 10. I come get the same deal, ticket number 10, because I haven't looked at the person who came simultaneously, right? So the task that came simultaneously. So we can both get ticket number 10. Okay, that's the first issue that we have. So how do we solve this issue? Well, we can break a tie. Even when the tickets are the same, I can still compare by the task ID number. So if, let's say, the ticket matches number J equals to number Y, then I'm going to look and compare J and Y. So now I have this kind of pair comparison. But, so the idea here is just I'm adding, when they're equal, I'm going to compare J and Y indices. And by doing this, I can break the tie, and now the the task that has a low index will go first. So now this problem is solved, but it's still not on a full the issue completely, because it's still non-atomic in the sense that I'm reading non-atomic. I can break the tie, okay, that's fine. But how do I deal with the fact that I'm reading and setting these things non-atomically? Well, the idea here is that the second solution to this, right, so that we have to implement, is to use this choosing array. So it's effectively a mini critical section here. So while I'm choosing the number, I have to tell other threads, oh, please don't look at my number. I don't know my ticket number yet. I'm looking and I'm trying to find out my ticket number. I don't know what my ticket number is. I'm going to be calculating in a second, but while I'm calculating, please wait. So that's like a mini critical section. So I'm setting choosing Y to true, then I'm calculating the ticket number, and then I set choosing Y to false when I'm done with this. So, and guess what? So the other threads will wait. So they will wait while I'm choosing J. So that means they cannot reliably use my number. They cannot say, okay, I can look at this number and make any judgment based on that, because the number doesn't contain any valid information yet. I'm trying to calculate my ticket number, but while I'm doing, I don't have anything. So effectively, while I don't have anything, other threads will be waiting. They'll be stuck while choosing J. Only when I finish my calculations, they will look at my number and they will make a certain decision based on that, right? So that's the way it works. So there are two solutions. One is to break the tie, and the other one is to create some sort of mini critical section to protect calculation of the number. So other than this, it's going to be the same as we previously discussed. You choose this ticket number, you yield it to everyone who has a smaller ticket number, and then when it's finally your turn, you're going to enter the critical section. So it's a little trickier, as you can see, and all these concurrency algorithms are typically trickier. So this is something to keep in mind when we learn concurrency. And I think this is important, not so much because we can implement logs, because definitely we don't implement logs like this well, certainly not anymore, right? So we have special hardware instructions for that, and there are some problems with this approach in modern computers, right? But I mean, it's still important to learn these algorithms, because they give us an idea how we can solve this. Something that seems to be impossible to solve actually can be solved with this very smart strategy, right? So you just use a different array, you kind of break ties on something like this, right? So those are really important techniques to learn. Okay, so let's look at the bakery algorithm and what properties of the bakery algorithms are. Well, I'm putting aside the stores and loads that can be important, but as I said, with modern computers, it's a little bit tricky, because anyway you don't have sequential consistency. I guess one thing to keep in mind that there is that numbers can grow unbounded. So how can that happen? Like the ticket number can really don't have any bound. I mean, clearly, if if everyone exits the critical section, they're gonna reset number to 0, right? So, and that means the next time someone tries to enter the critical section, assuming that all tasks exited the critical section, the ticket number will be 1. But it's also possible that the ticket number will just keep growing, and will never go back to the original state. So when is it possible? Can anyone give me an example? Any volunteers? We don't have any volunteers today. Anyone can make an example? Okay, someone has asked a question, right? Let me see. So what is the question? Just to clarify, you said we have a choice of either breaking the tie or creating an inner while loop. No, that's not a choice. We have to implement both, right? We have to implement both. We have to have the choosing array as well as breaking a tie. Just two things that we need to solve with non-atomic reads. Does it make sense? Okay. Yeah, so okay. So yeah, so those things are necessary, right? This is how we solve this the fact that it's non-atomic. Those two things are necessary. Okay, how can it grow unbounded? Well, very easily. Let's say we have py maybe a current task as a ticket 10. Then another task, then this task has not entered the critical section yet. It's waiting maybe for previous task. Another task comes, it gets ticket 11. Maybe finally the task with ticket 10 enters, but with ticket 11 still waits. In the meantime, another task comes, it gets ticket 12, and so on, right? So, and that way, ticket number will keep growing further, even though tasks are previous tasks completing. But if we have that kind of order pattern of execution, the ticket number will only keep growing. It will never go back effectively, because the maximum number will keep increasing. So in that case, I mean, if you have a 32-bit integer, you will easily overflow that integer. You will get like you have 4 billion states. In the modern computers, it can overflow in a matter of seconds, right? So, and therefore it may create some issues, because then now you cannot reliably check the ticket number if it overflows. Yeah, so for 64-bit integers, I guess it's less of an issue. It probably will take 100 years to overflow, at least on modern computers. Maybe on like computers that will have in a few years, it will not be the case, but I mean, at least as of right now, it will take hundreds of years. And 64-bit integers probably will be more reliable and more reasonable here. But, anyway, this is just something to keep in mind, that potentially can go unbounded because tickets are not going to be necessarily going back. And, ticket number can easily exceed the total number of processes that you have. So yeah, there is no limit to how far this ticket can go. Okay. So now let's talk about hardware support for Mutex. So yeah, I said that we can solve this problem with a software solution, but unfortunately, that doesn't really work well. I mean, if it was, I mean, by the way, can anyone tell me another problem with this algorithm? Is there any issue with this algorithm aside from the fact that we don't have this kind of sequential consistency? Like, is there any problem with the fact that I have to create this arrays of variables? Just any guess, right? So I think it's a relatively easy question. Can anyone answer this question? Anyone? Okay, we don't have volunteers today. Okay. Yeah, so what is the problem here? The problem is that when we have an array like this, what may happen is that you'll easily, like, I mean, I have to know in advance how many tasks I'm going to have in my system. Have to know, like, okay, I have 10 tasks, 20 tasks, and so on, right? I have to know in advance how many tasks I'm going to have. You know, that's really hard to tell. And that means for every task in the system, I have to provision when I create a log. I have to know, let's say I have 100 tasks, I have to allocate memory for 100 entries in the array. And that's going to be for every single log that I have in my system. So that's another issue. That's kind of usability issue. I don't know how many tasks I'm going to have eventually in my system. And also the fact that I'm going to be using of n memory because it like uses 2n shared variables. I would prefer to have some constant memory of 1, which is independent from the number of tasks. Yeah, and it's not that great that it uses O of n. So that's another issue. And by the way, that's an issue with all this kind of software-based algorithms. So what can we do? Well, in the modern computers, we have special hardware support. We have a special instruction which will effectively do multiple things at the same time. It's sometimes called read, modify, write. So read a memory location, do some operation on it, and then write the result. Well, I say modify doesn't necessarily means really modify. It may do some comparison, any operation. Probably say read up some operation and then write. So what we can do, we can test memory word and set a value. That's one possibility. Swap contents of 2 memory words. That's another. We will look at this in a moment. And that means that now we can go back to the original log implementation when we had to do several things simultaneously, and we can eliminate this gap and therefore devise a log using much simpler approach than just with load and stores. So let's take a look at the test and set instruction. That's a common instruction that is, you know, one way or the other is available in most computers. So what you're gonna have effectively the pseudocode, and by showing the pseudocode, I really mean this is not something implemented like in C, like here, right? But it's really implemented in hardware, and it's done in an atomic way. So it means all these things are done atomically. All these pre operations that are shown here, they are done atomically, so without within a single instruction. So we have test and set. It has the Boolean target value. So this is the memory that we're going to modify. So it's going to read the previous value from that memory location. It's going to read the current value of this location. Then it's going to set this memory location to true. And then finally, it's going to return the previous value that it read. So it reads the previous value, set it to true, and returns the previous value. So that's the idea of test and set. So let's see how we can implement a lock using test and set. So we have shared Boolean variable lock like previously. We initially set it to false, like in that incorrect example that we had in the past. Okay, so now let me go back to that example. Where did we have it? Yeah. So we set lock to 0 initial, and then we had while lock is 1, and then lock to 1. So now how can we eliminate this gap? The way that we eliminate this gap is this. We use this test and set instruction. So lock initially is false. And remember, test and set is going to set it to true and going to return the previous value. So, okay, if it was false, it's going to return false, but it will set it to true. So test and set will set it to true, but it will also return the previous value false, and that means it will break from the loop and will enter the critical section. So now the second thread, when it comes, it sees that the lock is set to true, so it will execute test and set as well. The previous value will be true, and the new value will be true. So effectively, the value has not changed. It's changed from true to true. So the previous value is true. So therefore, it will still spin. until the previous value becomes false. And when does it become false? That becomes false at the end of the critical section. This is when we reset it to false. At that moment, some thread that was executing test and set, just one thread that was executing test and set, will see that the previous value is false. It will set atomically to true, but it will also break from the loop because the previous value is false. So this is how we combine these two operations. Now there is no gap between check and because we set in the true value and also returning the false value, right, at the same time. So there is no gap anymore, and there is no way that some thread can get preempted in the meantime. So this is why it's going to be a valid log implementation, and this is how we can implement a log. So now there is some variations of this instruction. There is sometimes swap instruction, and swap will set to any value that you want. So it will return the old value and will set the new value, right? So and it will do it atomically. In case of x86, this instruction is known as exchange. So exchange will always return the previous value and set the memory location to a new value. So by using this instruction, you can implement a lock. It's like a very simple implementation, very straightforward, but it requires a special hardware support. But this is something that we actually use in practice, in practical implementation. I mean, previous algorithms are very important for understanding the concurrency problem, but they are not actually used in practice anymore, right? But this is something that is used in practice, so something to keep in mind. Okay, any questions? So any questions about test and set? Okay, I suggest that we use the remaining time, and if there is no questions about the lecture, let's use it for project 2. Do we still have, yeah, we still have 10 minutes. In case if you want to discuss project 2, do we have any questions about project 2? No questions about, oh, okay. Okay, somebody asks about question 4, right? Okay. Let me check. Okay, yeah, let's discuss question 4. Give me 1 second. Let me open it. So can you see my slide? Can you see the question 4? Okay. Yeah. So just to remind you, right? So in question 4, recall that this level 4, level 3, level 2, level 1, this is something that you have implemented in question 3. That's still gonna stay. So that's you're gonna keep the way it is right now. So now for you and add in, so remember this one is only kernel accessible mappings. This is one-to-one mapping. That means virtual address equals to physical address for the first 4 gigabytes. And here, but the only catch here, the only caveat here is that it's only accessible in kernel space. It's definitely not something that we don't want to reveal to a user program. So in user program, we only want to reveal pages that belong to this user program, that not your entire physical RAM. So for that reason, we have to create a separate mapping for user program code as well as for user stack. So the idea here is that because we have a multi-level page table, we can have large gap, like we can have 4 gigabyte when we create initial mapping, then a huge gap after this, and then we can create a user mapping. And what I'm asking you, let me draw the virtual address here. In the last 2 megabytes of your virtual address space, you want to map two user space visible pages. One is the user program, which contains the code that you need to execute, and the other one is user stack. So let's say this is your virtual address. So when you have like, remember how you can split this one points to here, this one points to here, another piece points to here, like level 2, then you have final level 1 piece. So that's how you can split virtual address, and then that is the offset. The offset is not like just carried over directly. So here, what you have to keep in mind is that, let's say you have last 2 megabytes, that's going to be, let's say 1111, all ones, right? All 9 bits once here. The same is for here, all nine bits set to 1. That means it's entry 511. You're gonna go to this last entry here, last entry here, last entry in level 2, and then for level 1, I give you some flexibility. I put a question mark here. So that's up to you to decide which one you want to use. So you're allowed to use last 512 entries, last 512 pages. So this one, anyone you can use, right? So just keep that in mind. So that this is how virtual address gets carried over to level 4. So I noticed that some of you are confused about level 3, level 2, and level 1. Remember that level 3, the only level 4 is the same. Remember that, right? So remember, only level 4 is the same because that's the root of your tree. That's only one page. And level 4, it's the only level that has 512 entries. Everything else is entirely different. On level 1, level 3, I can have different pages for level 3. For level 2 is also the same thing, and not to mention for level 1. Those are entirely different pages. So in level 4, I'm going to create in the last entry user mapping. Now, of course, for user mapping, level 3 is going to be different. Don't modify the one that you create in question 3. That's still going to stay the same way. Create a new level 3 where you're going to use the page, initialize everything to 0 except the last entry. The same is for level 2, initialize to 0 except the last entry. And then you create these mappings. So some of you ask, okay, where should I put this? Should I put it before level 4? Should I put after level 4? Again, it doesn't really matter because as long as this address points to level 3, this address points to level 2, and so on, that shouldn't matter. I mean, you can create level 4, then allocate 3 extra pages after level 4. That's going to be level 3 for user, level 2 for user, and level 1 for user. You can do it before level 4. It's up to you, as long as the addresses that you're going to put in the page table are correct. Remember, if you are a CPU, you're loading the address to level 4. That's the address, the top level address that you're loading. Then you're following these links and going to the corresponding levels and find the corresponding physical entry here. So that physical entry with the permission bits in the level 1, right? So this is when my final page translation entry is found. So that is something to keep in mind. So please don't confuse that. Yeah, okay. So let's see how much time we have. Okay, we have like 3 minutes. So just make sure you allocate this. Again, you have to initialize 512 entries, entire 512 entries. If you are not using some entry, initialize it to 0. Everything should be initialized. So now if you go to level 1, let's go to level 1, right? And let's say I want to map this last page. I want to know what the virtual address of this last page is. So I told you that you can use 2 to the power 64 minus 4096. That's going to be your last page. But obviously you cannot represent 2 to the power 64 because on modern computers, you will have 2 to the power 64 minus 1, right? That's the largest number that you have. So that is 0, basically. That's like with an overflow, it's going to be 0. So 0 minus 4096, that is basically minus 4096 L. that is your address. So I say L because use the lon that indicates it's an 8-byte integer, 64-bit integer. Because by default, if you put minus 4096, it's going to be 4-byte, 32-bit integer. You don't want to rely on the compiler to do any conversion. So make sure that you kind of specify it explicitly, minus 4096L. And then you can cast it to void star or something like this. So that's going to be an address of your last page. I mean, the page preceding this is going to be minus 8192L and so on, right? So you remember that up to our last 5 to 512 pages you can use any of them. Just make sure that those that you don't use you initialize to 0, but those 2 pages that you use for user program and user stack, you initialize correctly. Again, uprogram contains the physical address, treat it as the physical address, but user underscore program is going to be your virtual address. The same as for user stack and ustack. The only thing that for ustack, you have to adjust it by 4096, you have to subtract, then once you map, your virtual address has to be added for 4096 back. That I covered, I think, in lecture 20. Please take a look at this one more time if you are still confused about user stack. But otherwise, it's not different from user program. So you create these 2 mappings, and now your user program has this mapping. It's critical to have user space mapping, because without this stuff will not even work. So the reason why it works right now for question 2 and question 3, why you actually see some user space messages, because I'm creating this mapping for you, but I'm not giving any points for that. You have to implement it yourself in question 4 to get points for user space mapping. So once this is implemented, and this has to be implemented no matter what, right? Otherwise, stuff will not work. Again, as I said, I'm just doing it on your behalf when you are not implementing it correctly. And this is why you still see these messages on the screen.